What we're going to be doing now is describing a process that is important and integral to calculus. See what I did there? We're finding the area under curves, and to start we can use some geometric means to do this. So if I have this line, which is the line y is equal to x over 2 plus 2, you can verify that if you'd like, and I want to find the area of the curve between x equals 2 and x equals 4. What I'm finding is the area under the curve. Under the curve means between the curve and the x-axis. So you're going to see that referred to very, very commonly. It means this area right here. Well, if each of these squares is a unit, we can do this just simply by adding 1, 1, 1, 1, 1, 1, and then this whole thing would be 1. So that would be 7 units. You can also just do the area of the trapezoid. Area of the trap would be equal to the average of the areas, so 1/2 the average of the two sides, 3 plus 4, times the height would be 2, and that would also give me 7. So moving on to this one, we have the area under the curve here, and notice how here it doesn't give limits. Well, really what we mean is between -3 and 3. This is a semicircle, and if I did the area of the semicircle, that would just be 1/2 the area of a circle, not 1/3, 1/2. So 1/2, and the area of the circle is pi times the radius. Radius would be 3 squared, and I end up with 9 pi over 2. Moving on, we have this, find the area under the curve x squared plus 1 between x equals 0 and x equals 4. So if I have kind of x equals 0 here and x equals 4 there, this is going to be somewhat problematic because now I don't have a formula that's going to give me this area. So what I can do is something called the rectangular approximation method, or RAM, and that's the RAM that you're going to see several times in this lesson, the rectangular approximation method. And what I kind of have to doing is I'm going to actually model what this area is by rectangles. This is going to be very, and I know you're going to think about this is going to be very inefficient. However, there is a purpose for why we are doing it this way, so I need you to kind of go with me on this one. We're going to do the first type of this, which is called right rectangular approximation method, or RAM. And in right rectangular approximation method, the top right of the rectangle is a point on the graph. So let's look at this, and I'm going to want to basically do this with, well, I've got a region here. We're going to do this with n equals 4 rectangles. We're going to do that because this is split nicely into fourths. So if we have n equals 4 rectangles, then I can go, this is going to be one of my rectangles right here. And you may say, well, my rectangle actually went above the curve. Well, that's okay. But notice how the top right of the rectangle is a point on the graph. That is my first rectangle. Then I'm going to continue this pattern. I'm going to look at the next one over here and draw a rectangle. And then the next one right here and draw a rectangle. And finally right here and draw a rectangle. That is n equals 4 rectangles. And I'm going to want to compute the area of these rectangles. The area would be equal to, well, the width is 1, so 2 times 1 plus, now I need the function value at 2. 2 squared plus 1 is actually 5. 5 times 1 plus 10 times 1 plus 17 times 1. And again, where I'm getting these points, this is the ordered pair for 17. This is the ordered pair, not 10. This is the ordered pair 3, 10. This is the ordered pair 2, 5, and then 1, 2. So that tells me the heights of the rectangles. And if I add up all of those different areas, I'm going to get 7, 17, 34 units squared. And I believe it's easy to see that this 34 units squared is an overestimation of the actual area. Pause for just a second. Okay, resuming. Now, moving right along, we have this one, and where it's the same curve, but instead of doing LRAM, or RRAM, we're going to do left RAM, left rectangular approximation method. And in LRAM, as we call this, the point that's on the curve is the top left point. So we're going to draw the boxes differently. And it's going to take just a little practice drawing these boxes to get them right. But the top left one. And I know our rightmost rectangle doesn't reach the same heights as this, but we can still figure out that according to this method, the area is, so this is 2 times 1 plus, plugging in 2 gives me, this is a height of 2, plugging in 3 gives me a height of, let's see, 3, 5, so 5, and then 4, 10. So if I add up all of those, I get 2 plus, sorry, this first one was not 2, that was 1. That's a height of 1 right there. Add up all of those, I get 18 units squared. So this is, compare the two of them. Clearly the one before, this was an overestimation. And you can see that by the graph. This one was an underestimation. And the area is going to be somewhere in between that. Probably not the average of the two, but yeah. So in the previous example, the heights of each rectangle was found by using the rightmost endpoint of each interval. Sorry, that is an example of RRAM, and we did the LRAM too already. I probably need to modify this text here a little bit to include that. The last one that we haven't done is where we use the midpoint of each interval, and that's called MRAM. And I want to do that on the next of the next two examples. It also says, regardless of the method that is used, the width of your rectangles is always calculated in the same way. And the width is the lower endpoint, difference of the lower and the upper endpoint divided by the number of rectangles you want. Now, you guys are mathematically astute enough to know what I mean by that. We're going to do this with 4 methods here, or 3 methods: RRAM, LRAM, and MRAM, to calculate the different portions of this. So it says to do n equals 4. It's not always going to be the same number of intervals as boxes that you have, but here it is, so it's very nice to draw this. RRAM, if we draw it, is going to look like this. And really, when it comes down to it, what you have to know is the function values. This is the curve y is equal to root x, and we want to go from 0 to 4. So this point right here is 1, 1. This is the point 2, root 2. This is the point 3, root 3. And then this is the point 4, 2. And if I calculate the areas now, I would have 1 times 1 plus root 2 plus root 3 plus 2. And then that would give me a simplified version of just 3 plus root 2 plus root 3, which if I calculated that in a calculator would be about 6.146 square units. Okay, now when we do LRAM, you're going to notice that this one looks a little weird. My first rectangle actually has 0 height. My second rectangle now does this. My third rectangle now does this, and my fourth rectangle does this. So if I calculate the areas of those, it's going to be similar to what we did, but it is 0 plus 1 plus root 2 plus root 3, and I get a simplified version of 1 plus root 2 plus root 2. If I plug it in, I get 4.146 units squared. Okay, lastly, MRAM is to take the middle values. This one's a little bit more difficult to compute. So I'm going to do the middle of these, and so we get this, 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 and this, and it's the middle x value. So my function value right here is this is actually f of 1/2 plus f of 3/2 plus f of 5/2 plus f of 7/2, and each of those is multiplied by the width of the rectangle, which is just 1, if I'm adding up all the areas. So the square root of 1/2 is root 2 over 2, plus square root of 3/2 is root 3 over root 2, which is actually the same as root 6 over 2, then root 10 over 2, then root 14 over 2. And if I add up all those, I get an area that is about 5.384 units squared. So that, if you kind of look at how it's happening, this makes sense. You would think you would agree that MRAM is the closest of all of these, given these curves, but it's still not going to be the exact area. A better one, a good one to do, is actually called Trapezoidal Rule. This is a fourth type. Instead of using rectangles, we're going to use trapezoids. And I'm going to kind of skip over this explanation a little bit. You can read this, but I want to show you what a trapezoidal rule looks like. This is to use with n equals 5. We're going to go from x equals 0 to x equals 4. So this is going to be a little bit more difficult than it sounds. I'm going to create kind of a vertical line here at x equals 4, but I'm going to do intervals of, so if I have 4 minus 0 over 5, my intervals are 4/5 in width. So if it's 4/5 in width, then right here I would go, this is 1 interval at 4/5, then we have 1 at 8/5, then I have 1 at 12/5, then I have 1 at 16/5, and then finally up to 4. So that gives me intervals, and this is my first case of where my intervals are different than just kind of strict ones. Okay, we're going to zoom in a little bit. What I'm actually going to do is connect points. I'm going to draw points at each of these places, and I'm going to connect them with straight lines. So here to here, here to here, here to here, there to there, and there to there. Those actually form 5 trapezoids. This is 1, 2, 3, 4, 5. And I'm using trapezoids to model this. Clearly, you should be able to see that the trapezoidal method is going to be an overestimate of this as well, but it's going to get really, really close to it. So my area total is the sum of each of these trapezoids. So the area formula for the area of a trapezoid is 1/2 base or height times base 1 plus base 2. And my bases are my two different lengths here. So I'm going to do 1/2 times my height is 4/5 times the first trapezoid would be f of 0 plus f of 4/5. And we're going to add up all the different trapezoids after that. So to give you an example, the next one would be 1/2 times 4/5 times f of 4/5 plus f of 8/5. Well, if I add them all up, what I can actually do is factor out the 1/2 and the 4/5. What I'm going to be left with is f of 0 plus, you're going to notice that this f of 4/5 gets added twice to f of 4/5 plus, that's going to be true for every one of the middle ones, f of 8/5 plus 2, f of 12/5 plus 2, f of 16/5, and then finally plus the last f of 4, f of 20/5. The last one gets added once because if I look at how I take the trapezoids, this is one trapezoid, this is another trapezoid, this is another one, that's another one, that's another one. In those widths, your middle numbers get added twice because they're part of two different pieces, whereas your outer and inner numbers get added once. So this is going to be 2/5 times f of 0 is 1 plus 2. F of 4/5 is to square 4/5, so 16 25ths plus 1, because the function is to add 1, plus 2, square that, 64 25ths plus 1, plus 2 times 144 25ths plus 1, plus 2 times 256 25ths plus 1, and then plus 4 squared plus 1, 17. So next what I can do is just some almost trickery where I try to use some solid math skills to add this really quickly. This is going to be 1 plus 2 plus 2 plus 2 plus 2 plus 17, so that's 3, 5, 7, 9, 17 is going to be 26, so that's all the constant numbers, plus, and then I'm going to do 2 times, let's add up all the fractions, 80, 80 plus 144 is 224, and then 224 plus that is 480, so I have 480 over 25, which is going to give me 2/5 times 26 plus 960 over, well, I should probably simplify the 480 over 25 by dividing by 5. So 5 into 4 to 80 is 9. 96 over 5. That is the same as 2/5 26 plus 192 fifths, which is, let's see, 52 fifths plus 384 25ths. Multiply this by 5, you get 260 plus 384 all over 25, or 644 over 25, which is about 25.76. Now, you're going to kill me on this, because what you're going to notice if you do this enough is that this area is also the average of LRAM and RRAM. So if you have a problem that asks you to find LRAM and RRAM and then trapezoidal, it's probably easier to find LRAM and RRAM first and then just do its average. Okay. Last point of this, it says, in recent years, the AP exam has gotten away from equal interval widths and asks that you approximate the area using interval widths that are not equal. So to do that, if we're going to approximate the area of the curve here, basically what I want to do is plot the points that it's giving me. So 0, 3, then 1.52, then 2, 4, then 3, 8, and then 5, 6. So I have the points plotted. I'm going to do the same points on each of these. So 0, 3, 1.52, 2, 4, 3, 8, and 5, 6. And then we draw the LRAM this way, then this way, then this way, then this way, like that. I would draw RRAM like this. Sorry, I'm missing the 3, 8 point. That was right here. And like that. MRAM we can't do, and you'll kind of see why that is. Trapezoidal we can. I'm going to go from, see, there's a point here, so like this, then like that, then like this, and then like that. So I'm going to leave the calculation of these areas up to you. This would be 25.5 this would be 25. The trapezoidal, if you calculate in one of two ways, you either do it manually by calculating each trapezoid, or you know that the average of the LRAM and RRAM is 25.25. So that is the last one. I'm not sure why I repeated that page. I did, but that's it.